Welcome students. Today we'll be talking about the next model of the nucleus that we have to discuss, that is the shell model. So we talked about the liquid drop model of a nucleus in the last lecture, and as we have discussed, the liquid drop model is a model in which we consider a collective behavior of all the nucleons in the nucleus. The nucleus is considered to be analogous to a liquid drop. And this model, that is the liquid drop model of a nucleus, was successful in explaining quite a few of the bulk properties of the nucleus, like the binding energy of the nucleus and how it varies with the mass number of the nucleus. Then it could explain the processes of fission, fusion, radioactivity, etc. However, certain other experimentally observed properties were there which the liquid drop model failed to explain. For example, different nuclei, they were found to have nucleus spin, finite nucleus spin, which can be experimentally measured. They also had magnetic moment, electric quadrupole moment. All these, the liquid drop model failed to explain. Also, for lesser mass numbers, it was seen that for particular values of mass number, the nuclei, they showed exceptional stability, and there was some erratic variation of the binding energy per nucleon for lower mass numbers. These were some observed properties of the nuclei which the liquid drop model failed to explain. So a need was felt for another model of a nucleus in which we don't treat the nucleons collectively, we treat them individually, and hence the shell model of a nucleus came into being. So it's a theoretical model of the nucleus which is used to explain certain observed properties of the nucleus. So in this model of the nucleus, it assumes that the nucleons inside the nucleus are grouped together in energy shells in the nucleus, similar to the electron shells in an atom. So this model of the nucleus, that is the shell model of the nucleus, is inspired by the electronic shell structure, in which the electrons revolving around the nucleus, they reside in energy shells, and being fermions, each energy shell can have only a fixed or limited number of electrons governed by Pauli's exclusion principle. Similarly, it was thought that the nucleons inside a nucleus also they reside in energy shells. This is one basic consideration of the liquid shell model of a nucleus. These shells are regarded as filled when they contain a specific number of protons or neutrons. As I told you, the number of nucleons in each shell is limited by Pauli's exclusion principle. Why? Because these nucleons, they are fermions, and hence they have to obey Pauli's exclusion principle. The shell model is also referred to as the independent particle model, as it assumes that each nucleon inside the nucleus moves independently and is acted upon by an average field produced by the interaction of all the nucleons. So this is again like the inspired by the electronic shell structure. The electrons in their orbits, they move under the influence of the electrostatic potential. They are under the influence of the electrostatic potential. They are bound to the nucleus by the electrostatic force. And we treat the electrons independently. They move independently in their orbit. Similarly, it was proposed in the shell model that the nucleons also, they move independently or independent of one another. But however, unlike in the case of the atomic electrons, the field here is not known. In the case of the electrons we know it's the electrostatic field, but here what is considered is that the nucleons, they interact among themselves via the strong nuclear interaction. This interaction gives rise to a field, and under the influence of that field, the nucleons, they move about the center of mass of the nucleon system. So it's like by the nucleons for the nucleons. What I mean is that the nucleons, they interact among themselves, giving rise to the field, and under the influence of that field itself, the nucleons, they move. So what are the evidences of the shell model of the nucleus? Before we go into the details of the shell model, develop the theory of the shell model, there were quite a few evidences which suggested the existence of the shell structure inside the nucleus. The primary evidence of the existence of the shell structure within a nucleus is the occurrence of magic numbers. It is observed that nuclei having certain specific number of neutrons or protons have very high stability than those having one more or one less. So these number of nucleons at which the nucleus shows very high stability are known as magic numbers. So these are experimentally observed, and this is the reason for the erratic variation of the binding energy per nucleon with mass number, the binding energy curve for lower mass numbers. So at particular numbers of either protons or neutrons or both, the nucleus shows very high stability. So if one more or one less, the binding energy per nucleon will be comparatively much lesser than the nucleus having these numbers of protons or neutrons. So these magic numbers experimentally found are 2, 8, 20, 28, 50, 82, 126 and so on. The liquid drop model could never explain why the nucleus or any nuclei at these numbers of protons or neutrons or both, they show very high stability. Then the naturally occurring isotopes, or rather all the other evidences that we talk about for the shell model, are related to the magic numbers. The naturally occurring isotopes whose nuclei contains a magic number of protons or neutrons have greater relative abundances in nature. For example, the isotopes 88 strontium, here N is equal to 50, 138 barium, N is equal to 82, have relative abundances of 82.56% and 71.66%. So this is because these nuclei of these isotopes, they have magic number of neutrons and hence they are very stable. So comparatively much stable and hence their relative abundances are high. The number of stable isotopes of an element having magic number of protons is large compared to those of other elements. So this is under evidence of the shell model. The neutron capture cross section of nuclei with magic numbers of neutrons is usually low. So capture cross section means when neutrons are incident in a nucleus, the probability of the neutron being captured by the nucleus, that probability is given by the cross section. So what is a cross section? This is a parameter which gives us the probability of that particular nuclear reaction, or for that matter any reaction taking place. So what has been found is that the nuclei having magic number of neutrons, they have very less probability of capturing a neutron which is incident on it. This can be explained only by considering that the neutrons, they reside in shells and the shell is filled at these numbers of neutrons, the magic number of neutrons, and hence they have very less affinity for another neutron. From the electronic structure, atomic structure, we can think about the noble gases whose shells are filled and hence they show very less reactivity. Similarly here, also Nuclei with magic numbers of proton have very low proton absorption cross section. So if proton and neutron shells are filled, so these nuclei will have very less affinity for absorbing another proton or a neutron. The stable end products of all the three naturally occurring radioactive series are the three isotopes of lead: uranium series, actinium series, and strontium series. These are the three radioactive series we are talking about. Radioactive decay starts with that nuclei, intermediate steps are there, and ultimately the final stable end product in all these three naturally occurring radioactive series is found to be lead, different isotopes of lead. And lead, it happens to have a magic number 82 of protons. So now we need to develop a theory for the shell model of a nucleus. To develop a theory for the nuclear shell model, it is necessary to assume the existence of a potential within the nucleus. So as I was talking about, in the case of the atomic electrons, we know that the electrons, they move under the influence of the Coulomb potential. However, in the case of the nucleons inside the nucleus, we don't know what is exactly the kind of the potential under which the nucleons are moving. So to develop a theory, we need to assume the existence of a potential. So that's what I was talking about. Unlike in the case of the electrons, the type of the potential under which the nucleons move is not well defined. It is assumed that the nucleons interact among themselves, giving rise to an average field. Under the influence of this field itself, the nucleons, they will move. So this nominally spherically symmetric central field of force governs the motion of individual nucleons. Because of the spherical symmetry of the problem, we consider the potential to be spherically symmetric, under the influence of which the nucleons, they move. So using this potential, the Schrodinger's equation governing the motion of individual nucleons is solved. So that is the basic pathway in which we deal with a problem in quantum mechanics. Particle moving under the influence of any potential. What we do, we write down the Schrodinger's equation, solve the Schrodinger's equation, write down the Schrodinger's equation, knowing the potential, solve the Schrodinger's equation, and get the energy eigenvalues, which will give us the energy structure of the system. So same is done in this case. Different forms of potential has been used for calculation of the nuclear energy levels. People tried with different kinds of potential. However, the best fit with experimental results is obtained by using the three-dimensional harmonic oscillator potential of this form. So this is a potential, harmonic oscillator potential. This is the standard potential. Using this potential, the Schrodinger's equation for the nucleons is written down and is solved. So the three-dimensional Schrodinger's equation is solved using this potential with the total wave function. We can write it as with this is from quantum mechanics, quantum mechanical theory. The Schrodinger's wave function has a radial part and an angular part. It can be written in this form. So we are not exactly going to solve the equation, Schrodinger's equation, at this level. This is a problem of quantum mechanics. So what we'll be doing is we'll be discussing the result of the theory. So after the Schrodinger's equation is solved using the spherically symmetric harmonic oscillator kind of a potential for the nucleons, the eigenvalues corresponding to the eigenfunction is obtained as E and L. These are the eigenvalues for the nucleons. Lambda plus 3 by 2 h cross omega, where lambda is equal to twice n plus of L minus of 2. Here n is the principal quantum number, L is the angular momentum quantum number. So the values of n can go from 1, 2, 3, etc. And the values of L can go from 0, 1, L is equal to n minus 1. So L goes from 0, 1, 2, 3 and so on. Therefore, the values that lambda can assume are 0, 1, 2, 3, 4. So, depending upon the value of lambda, the lowest energy state, lambda can be 0. So, the energy value for the lowest energy state will be 3 by 2 h cross omega for the nucleons. So, successively higher states, lambda is equal to 1, 2, 3, 4, etc. Here n represents the radial quantum number and n minus 1 gives the total number of nodes in the radial function. And L is the azimuthal quantum number. Thus, the system can have a discrete set of energy values E and L. These energy levels are usually degenerate. Means energy levels are degenerate means many sublevels will be there having the same energy eigenvalue. So what is the degeneracy? Let's see that. The angular part of the wave function has a degeneracy of 2L plus 1 for a given L. Why? Because for any given L can have 2L plus 1 ml values. So this 2L plus 1 corresponds to the magnetic quantum number. Further, each level of a given energy, that is given lambda, it contains several states of different NL. So if we see here, ENL is equal to lambda plus 3 by 2 h cross omega. So for a particular value of lambda, we can have different NL combinations which will give me the same value of lambda and hence the same value of energy. So that is what we are talking about. Given lambda contains several states of different NL. So the degeneracy of a state is actually the summation over L 2 into 2L plus 1 over different possible L values for a given lambda. So for a given lambda, we have to see the different NL values which will give me the same lambda. So for each value of L, we can have 2L plus 1 ml values. So that corresponds to a sublevel. So the total number of sublevels is given by summation over L 2 into 2L plus 1. The factor 2 is due to the two possible spin orientations of the neutron or the proton. So each of these summation over L 2 into 2L plus 1 degenerate states for a given energy having combinations of N, L, ML and MS values determines a sublevel of a given energy. So now according to Pauli's exclusion principle, each of these can be occupied by a nucleon of a particular kind. When all the sublevels of a given energy are filled up, we have a nucleus with a closed shell of neutrons or protons. So the different energy levels is degenerate states and the number of nucleons in each of these levels is shown in the table. So how it works out, let's see. So the different energy values, it depends upon the value of lambda. Lambda can be 0, 1, 2, 3, 4, 5, 6. So when lambda is 0, E can be 3 by 2 h cross omega. Now what are the different combinations of N and L that can give me lambda is equal to 0? There is only one combination, 1 and 0. If I put N is equal to 1 and L is equal to 0, I get lambda to be equal to 0. So this summation becomes summation over L. We have only one L value, that is 0, 2 into L plus 1. So that means 2 into 0 plus 1, that is 2. So the total number of nucleons that can be there is 2. Now for lambda is equal to 1, energy value will be 5 by 2 h cross omega. Degenerate states. What are the different combinations of n and l? Only one combination. N1 L1 gives me lambda is equal to 1. So this summation over L, only one L value. So 2 into 2 into 1 plus 1, 2 into 3, that is 6. So total number of nucleons for closing of this level of energy 5 by 2 h cross omega. So this level can have 2, this level, energy level, can have 6. So the total number of nucleons required for closing this level is 2 plus 6 is equal to 8. Now lambda is equal to 2. For lambda is equal to 2, energy is 7 by 2 h cross omega. So what are the degenerate states? Now we have two combinations of n and l which can give me lambda is equal to 2. So n can be 2 and l can be 0. So that will give me lambda is equal to 2. Similarly, n1 and l2 can give me the same value of lambda. Therefore, the summation 2 into 2l plus 1. So first case we put l is 0, 2 into 0 plus 1 into 2, that is 2, and next we put l is equal to 2. 2 into 2, 4 plus 1, 5, 5 into 2, 10, plus the other 2 gives me 12. You can work it out. So 12 nucleons can be there in this level, this degenerate level. Total number of nucleons that can be there with this value of energy is 12. So the total number of nucleons required for closing this shell is 2 plus, this is already 8, so this is 6 plus 2, 8 plus 12, that is 20. Similarly, 3, 2 combinations, total number of nucleons 20. So total number of nucleons required for filling up of this up to this level is 6 plus 2, 8 plus 12, 20 plus 20, 40, and so on. For lambda is equal to 4, we have 3 combinations of n and l. Total number of nucleons with this amount of energy, this level is 30, this is 70, and you can work it out. So what is seen is that it is observed that with the spherical harmonic oscillator kind of a potential, apart from the first 3 numbers 2, 8 and 20, there is no agreement with the experimentally observed magic numbers. Because the magic numbers are 2, 8, 20, 28, 50, 82, 126. That is what we discussed. Only the first 3 it matches with the experimentally observed magic numbers. So there is a lacune, there is some problem with the theory or the potential that we have considered. We are not getting the higher order magic numbers, only the first 3. So what is the problem? What was proposed is that in order to explain the higher magic numbers, it was proposed that at higher values of the number of nucleons, because of the interaction between spin and the orbital motion among the nucleons, the symmetry of the potential is distorted. So, a spin orbit interaction term has to be added to the central potential, VR, as considered earlier. We considered a spherically symmetric harmonic oscillator kind of potential. So what was considered is that because of the interaction between the spin and orbital motion among the nucleons, the symmetry of the potential is broken. So we need to add a correction term to the potential. So the spin orbit interaction term can be written as VLS phi r L dot S, where phi r is a potential function depending on the radial coordinate r, and L and S are the orbital and spin angular momentum vectors. So phi r is spherically symmetric function giving the profile of the potential. So basically what it means is the spin and the orbit interaction gives rise to a correction term to the spherically symmetric potential. So assuming strong coupling between the spin and the orbital angular momentum of each individual nucleon, we have a total angular momentum J for each nucleon as J is equal to L plus of S. Now we have L dot S is equal to half of j into j plus 1 minus l into l plus 1 minus s into s plus 1. This is from the rule of vector addition. So if j is equal to l plus of half, there can be two cases where l and s, that is the spin angular momentum, orbital angular momentum and the spin angular momentum, they are aligned in the same direction or they are aligned in opposite directions. So if both are aligned in the same direction, the total value of angular momentum of the nucleon will be L plus of half. So in that case, L dot S becomes equal to L by 2. And again, if J is equal to L minus of half, L dot S is equal to minus L plus 1 by 2. So what it basically means is that because of the spin orbit interaction, the energy levels, they split up. So the expectation value of the spin orbit interaction potential is, we can write it as VLS. So this is the correction to the energy eigenvalue because of the spin orbit interaction, can be written as this. So we can write it as L dot S phi r. So where phi r is the expectation value of the radial part of the interaction term. So for the two states, J is equal to L plus of half, ELS is equal to, putting it from here, L dot S is L by 2. So ELS is minus L by 2 phi r. And for J is equal to L minus half, L minus half. L dot S is minus L plus 1 by 2. So we put it here, we get ELS, the correction to the energy eigenvalue is minus L plus 1 by 2 phi r. So the spin orbit splitting of the two levels is then the separation between the two levels because of the spin orbit splitting is ELS L minus half minus ELS L plus of half. So that is equal to L plus 1 by 2. So what it basically means is that a particular energy level, because of the spin orbit interaction, will split up. It will split up into upper level and a lower level, and this is the splitting between the two levels. So we'll see. So what happens here is something like this. This is after splitting N, L, J. So 1 S half. So 1 is the value of N, L, J. So half is the value of J. So the first level, so this is the 1s level, L is equal to 0, no splitting. So here we are talking about splitting L plus half. So for the L plus of half and L minus of half, so for L is equal to 0, the 1s level, there is no splitting, so two nucleons can reside here. For the second level, 1p level, L is equal to 1. So L plus of half and L minus of half. So 1 plus of half gives you 3 by 2, J is equal to 3 by 2, and J is equal to 1 by 2. So what happens? This 1p level, because of the spin orbit interaction, it splits up into 2. So this sublevel now can have 4 nucleons. 4 in the sense, why? The number of nucleons in this level will be 2j plus of 1. J is 3 by 2, so 2j plus of 1 gives you 4. And similarly, 2j plus of 1 here, 1 plus 1, 2. So in this sublevel, there can be 2 nuclei. So this is the 1D level. The 1D level, it splits up into 1D 5 by 2 and 1D 3 by 2. But this is the 2S level, it doesn't split. So the 2S level can have 2 2 into j plus of 1 gives you 2, and 1d 5 by 2 can have 6. 2 into j plus of 1 is 6, j is 5 by 2. So all these sublevels, this sublevel can have 4. So the number of nucleons required for closure of this shell is 2. For closure till here, it is here 8. So what happens? There is a restructuring of the energy shell structure of the nucleons because of the spin-orbit interaction. So closely spaced energy levels, they constitute a shell. So the shell closure occurs at different levels. So let's see. It is obvious that the state J is equal to L plus of half lies below the state J is equal to L minus half. And the spin orbit interaction, it splits each of the higher single particle levels. The splitting increases with L because it depends ELS that we were talking about. It is dependent on L. The splitting increases with L and can become so large that for a given n, the term with the largest L value and J is equal to L plus of half can slide down to energies as low as those of the multiplet with quantum number n minus 1. What is meant here is you can see the splitting here. This is 1 G level. L is high for a G level. So J is equal to 9 by 2. It splits up into 1G 7 by 2 and 1G 9 by 2. The splitting is so big that this level with J is equal to L plus of half, it slides down and it becomes closer to the levels with, let me say, 2p level here, and it clubs together with this. So there is a restructuring of the energy levels of the nucleons in the nucleus. So this defines a new level, new closure of the level, and this slit, it is going up and it is with this group. So that is what is meant here, that the splitting increases with L and can become so large that for a given n, the term with the largest L value nj is equal to L plus of half can slide down to energies as low as those of the multiplet with quantum number n minus 1. So this level, as I told you, it comes back and clubs together with the f values n. N is equal to 1 here, and this is n is equal to 2. So this splitting is so high that this level it comes and clubs together with this. So there is a restructuring of the energy structure or energy levels of the nucleons. So in accordance with Pauli's exclusion principle, each sublevel of a given J can accommodate a maximum of 2J plus 1 nucleons of either kind, for which the magnetic quantum numbers Mj are different. Now the group of sublevels NLJ having energy values close to one another constitutes a shell. So there is, as I told you, reorganization of the shell structure of the nucleus. Thus, there is a reorganization of the whole shell structure. The reorganization of the shell structure is shown in the figure, and the occurrence of the magic numbers can be explained with the help of it. So what we see here is a shell closure occurs here. First one shell closure occurs here. Second shell closes here. The third shell it closes here. Fourth shell it closes here. Then the fifth shell it closes here. So we have total number of nucleons for closing of this shell is 2. Total number of nucleons for the closing of this shell can have 2, this shell can have 4. So 6. Total number for closing of this shell can have 2. So this is 8. 2, 6, 8. So the shell closures occurs at 2, 8, 20, 28, 50, 82, 126, etc. So this defines the magic numbers. So these are the experimentally observed magic numbers: 2, 8, 20, 28, 50, 82, 126, etc. So this shell model of the nucleus was very successful in explaining the observed magic numbers, that is the stability of the nuclei at particular values of magic numbers. Also, using this shell structure, we can find out the experimentally observed nucleus spins. So probably in the next lecture we'll be talking about that, how to actually determine the nucleus spins of different nuclei using the shell structure of the nucleus. That's all for this lecture. Thank you.